let's take a quick look here at finding a directional. It's another typo that should say derivative of this particular function, specifically at the point 2, 1. And we're claiming that we want this thing in the direction of theta equals pi over 4. Well, if theta equals pi over 4, cosine of theta is going to be, it's cosine of pi over 4, which is root 2 over 2, and sine is going to be also root 2 over 2. So we have our directional vector u, and that's going to be root 2 over 2, root 2 over 2. And notice if you find the magnitude of u, this is in fact a unit vector. Okay, so what I need now is I need to start looking for partials. So I'm going to start off by saying that the directional derivative with respect, or in the direction of u, of f, is going to be equal to the partial with respect to x times root 2 over 2 plus the partial with respect to y times root 2 over 2. See, this is where I'm getting my direction from. So let's go ahead and just let's just go for it now. So this is actually going to be equal to the partial with respect to x is going to be, well, let's just do some couple of components. So let's just scratch that out. So let's just take a look specifically at only the partial with respect to x. That is going to be 2x y cubed minus 0. And I'm going to evaluate this at 2, 1. So that means I'm going to have 2 times 2 is 4 times 1. So this is just simply equal to 4. And then I'm going to have the partial of y, which is going to be what? 3x squared y squared minus 4y cubed. Evaluate again at 2, 1. And that is just going to be, what was that? 3 times 4 times 1 minus 4. So that's 12 minus 4. I don't know why I did that. So that's 12 minus 4. So this is going to be 8. So this directional derivative will actually be 4 times root 2 over 2 plus 8 times root 2 over 2, which is obviously 2 root 2 plus 4 root 2. So that's just going to be 6 root 2. So what this is saying is that the rate of change with respect to z, okay, this is the rate of change of z, in the direction of pi over 4 at the point 2, 1 of this surface is positive, so it's going up. And that rate is 6 root 2. Now notice if I simply wanted a vector that starts at that point when x is 2 and y is 1 and heads off with this rate of change in this direction, I need to find z. So I need to find f of x, y, because then I'm going to have all 3 coordinates to actually find the very point that we're actually talking about. And that's going to be, see, 2 squared times 1 cubed minus 1. That is 4 minus 1, that's 3. So the actual point on the surface will be at 2, 1, 3. Now, I also know that I'm heading in this direction. So what I can do is I can consider the vector 2, 1, 3. You recognize this. This is the sort of thing we've done many times before. Plus t times root 2 over 2, root 2 over 2. And then, of course, in the z direction, the rate of change of the direction is 6 root 2. So now my vector is simply going to be 2 plus root 2 t over 2 and 1 plus root 2 t over 2 and 3 plus 6 root 2t. So when I draw that surface, I'm just going to draw something here. Let's just say that this is the point, and the direction I'm heading, the way I drew this is pretend like this is the curve that was carved out when I took this vertical plane in this direction. It's obviously just going to be tangent at this point in this specific direction. So what I'm going to end up with is this vector. When t is 0, I'm at this point, and this tells me the direction that I'm going. I'm heading up, and these give me my angles in terms of x and y. So I could actually draw this off the surface, which I already set up here. And I set up a couple of components. So I've got A, B, C, and D, and you can see my Mabel commands here. Here's my initial surface. And then this space curve is my vector that's going to start. Well, actually, I moved it out to make it start at, well, it started at 0. So when t is 0, so it's going to start on the surface. And let's just go t equals 1. And then I have an arrow that points to the point on the surface that we're supposed to be at. And then I've got this other arrow that is actually, this is u. This is my directional vector. Oops, I just noticed that's not quite right. I forgot my root 2 over 2. And this is going to be root 2 over 2. So there's my directional vector that's on the xy plane. So when I graph it, this is what I've got. So I should make some color changes here. Okay, I went ahead and made this vector that points to the point 2 and 3 green, and I changed this to 0, but I didn't hit enter, so it's still going from -1. So I just fixed that, and here we go again. So here's my surface. Here's the point that I'm talking about right there on the surface, and this is my directional vector. So what I'm looking for is the rate of change from my surface in this direction. So this vector right here, flip this around, this points in the direction of the rate of change from z at this specific point in this same direction as this unit vector. And you kind of spin this around a couple different angles, and you kind of get the idea of what's actually happening there. Now, the question is, really, is this thing parallel to this guy? Well, in the setup, we know that it is, but how can we convince ourselves? I'm going to go ahead and change this real quickly to back to -1 to make it a little bit longer. And I'm going to turn off A here. A is the surface. I want to get rid of the surface for a moment. But I do need, I need my axes back in there. So I'm going to put axes equals box. That'd be quick and dirty. So I have this boxed axes. Now what I want to do is, where's Z? I want to take my Z axes. So there's X and Y. I'm going to spin around here. And I want to look directly down on the Z axes to look to see if they're heading the same direction. Now, obviously, we'd have to make this considerably longer to truly convince. Whoops. Try to spin this around a little bit. To truly convince ourselves, which I can do. I can go and make this longer. I simply remove the 1/2 there. Because that 1/2 was square root 2 over 2. I simply dropped the 2 in the denominator because that's just a scalar. So this thing is twice as long as it used to be. And with that, when looking straight down the z-axis, I think, let's see if I get this a little bit better picture. I think it's probably easier to convince you that those guys really probably are parallel from this point on. Well, actually, all the way, obviously, but you get the idea.